Okay, welcome back to Chapter 9, Social Behavior of Behavior-Based Robotics. So, what we try to learn in this session is the benefits of multi-agent robot systems. We see what the characteristics are of those teams, and we see the difference between single robots versus multi-agent approaches. And that's important because nearly everything that we've done before is for a single robot, while in nature you more or less never see a single species. It's always in a group. So in principle also a lot should be with it available from behavior inside the group. And partly, if you think about it, why as humans we are so smart, not because we as individuals are that smart, but we can build a society where I as lecturer can bring some of my message across to you and further and further, and so get more and more advanced systems. Okay, so we'll start with the principles and then we'll look to nature again. So robot teams have some benefits. First, you can improve the system performance. What is the ideal that if you have twice as many robots, you can do twice as much work. Sometimes you can even do more than that. In other cases, it's slightly with it less, and it depends a little bit on the task and the environment. Some tasks are even not possible to be done alone. I work in the RoboCup rescue, and there you have firefighters that have to extinguish fires. And some fires are that fierce that you can put your water into it, but that this dams away, and you can better go with 2 fire brigade cars to a less fierce house and extinguish that and make sure that it doesn't catch fire, than just throwing all your water alone in a place where it doesn't matter anymore. So sometimes doing it together really makes sense. As a team, you can cover much more with the ground, so you can sense a much larger area, but you can also do works distributed. So that means that for instance, with soil in agriculture, you can with it do a far better job. And last but not least, if you have a team of robots and one of the robots dies, then you can still finish the task, while if you have a single robot, that's the end of the mission. But it's not all what it benefits. Once you have interference, robots can blockade each other and compete for the same resources. So you would have a lot of problems there. When you want to do work in a team effectively, that means that you have to start to communicate. Communicate can be seen as a sort of virtual sensor where you get additional information. But another robot may think that he has a good estimate of what he sees, but maybe he's completely off, and in that way sends the whole team over the edge as a sort of lemmings. Further, if you are working as a team, then you are doing some behavior, but a robot not always knows why some behaviors are activated. So it means that you have to start communicating what precisely the intentions and what not only what the other robot is doing, but also what he's trying to accomplish. And that can be, then you have to communicate on a meta level. And If you have a twice as big team, then probably also you have to spend twice as much money on your hardware. So it's not that easy to make really large robot teams. So you can look on different approaches how to organize such a team. First, it's logical. My colleague from the VU really loves that we have a sort of playground and a battleground where they first learn to behave and then learn to survive. You can also, we're really good in structuring our organizations to put some hierarchy into it and to make sure that the team works as a team. You can make sure that the cooperation between the agents is based or democratic by sending votes or by auctions where they bid for certain options. You can organize it, say, by money or by votes. A lot of efforts in the AI community is in distributed AI, where by multiple agents, each of them is making their own decision and also thinks what that means for the group. You can think of motion planning for one robot alone, but also as the whole team, as an one robot with multiple degrees of freedom and plan it for the whole. And last but not least, and it's something that was really popular in the last century, was artificial life, where you can see emerging behaviors from some quite simple rules and see which part survives and which ones declines. So the multi-robot systems have to work as a team. That can be cooperative if they have the same goal, but there can also be a lot of competition inside the team, for sure, if there is a limited number of resources. So when you get to the mushrooms for the first time, then you're the one that stays fit. You can also think of combinations where they start to adjust their behavior to each other. If you have a pursuit and evasion system, and there you can make a sort of equilibrium between it. And a lot of research has gone in swarms that are in principle quite, say, stupid teams of robots, but behavior-based, the emergent behavior as group can be quite complex. So what are the tasks that they have to cooperate or to compete on? Examples of that are typically foraging, consuming, grazing. You can do some flocking or formation. So flocking, you can have the members on the outside, on the outlook, and trying to protect the team. And you can, if you're not strong enough to transport an object on your own, you can together lift it with 4 people on each side of the coffin, and you can lift far more heavier loads. Okay, let's first look in biology what sort of lessons we can learn there. So cooperative behavior is quite it's common in the animal kingdom. The great examples are ants, bees, termites, and as a group they can build buildings that even termites are larger than humans, and you can even see from space. Also, in social biology, there is a lot of literature And what comes out from that is that most common is that you not raise as parents your children alone, but as society. So you have a cooperative caring for the offsprings. You often have that there is a benefit of standing higher in society because you have a higher productivity. What you also see is there's always multiple generations in one society, but also specialization is quite common with bees, the queen bee, with the worker bees, the soldier bees, etc., etc. And if you want to coordinate the behavior, then communication is the key. And that can be sometimes with really with it simple means, as others, or with it traces on the ground just by walking there, the elephant path, but also by dancing, singing, etc., etc. So there's a whole richness of different solutions the animal kingdom has thought about. So Tinbergen, our Nobel Prize winner, described several different sorts of social behavior. Part of it is simple, but part of them is more complex. So more complex behavior is the mating behavior. So he worked with the stekelbaarsjes, the small fish in the Dutch lakes, with how they did the persuasion, with the coloring, filling up, etc., etc. But there's a whole, say, dance with it to get to the mating. In the same time, you have a lot of group behaviors, getting together with it, discussing with it things in congregations, and signal each other when there is a danger, etc., etc. So fighting is not mostly not between species, but in between species, and it helps to determine the pack order. So, what sort of animal communication with it you see? Say the different six senses are that all use. Sound can reach quite a far distance. For instance, the whales can communicate all over with the ocean. But you have the backside that everybody can listen to what you're saying. So it's mainly with it for alarm. Luminescence. So you with it can the fish with it in a deep sea with it use that quite often. Chemical with it is great, but you mainly use that for mass communication. It's really broadcasting, but also reflecting light or tactile or electronical is all with it possible. So we also worked, say, with it on a lab with social behavior, and I wanted to show that what's possible there with robots. And we worked with a humanoid robot, and what's nice from this is that you see has the shape of a human, that you can easily interpret the affective state quite easily. And that's quite special, because you think that most of the recognition of the emotional state is on the sound of your voice or your facial impression. But this robot now, the one what our students working with, doesn't have any facial signals except for the color of his eyes. But you can still see that you can do a lot with your emotion there. So, what did we do there? what we learned from psychology, that there are 3 dimensions where your social feelings with it can go, and already with it other researchers have associated those with different emotions a robot could see. And the scenario that we wanted to play is that we want a robot, a humanoid robot, that is standing next to you while you're watching a soccer game and shows the right emotion on the right time. And the thing that what we did is that we asked a lot of colleagues what their emotional state, how they would change if during a soccer match the Dutch team missed an attempt, or that one of the attempts of the opponents was saved, and we put a number to that. And for each of those events we had a certain measure on valency, with it on ration, etc. And with it we would get there a rule what would happen. And the nice thing is that builds up. So during the game you get a lot of those events, and you starting to have in blue a travel through the emotional space. And on certain locations in the emotional space we connected to a body motion of the robot, and once you came near to such an area, then it showed that expression. And the results you can see here. Did I copy it? No, I didn't copy it. Okay, I will send to you later. Okay, so what you see is what actually happened during a game, and the 3 different emotions in blue, red, and yellow are visible, and you see a sharp peak every time that a core is called, and when nothing happens, that the emotions go a little bit down, and that's a very natural way to show emotions, and the people really was impressed. What was the hardest part from our side is to get precisely the timing right, how fast you get bored, how fast you don't get anymore, because about emotions a lot of said, but not with accurate timings to it, so we had to do that manually. So what we learned from this sort of experiment is because human robots can really look like a human, so then it's also for a human very easy to project emotions on the robot and to start understanding its perspective. And in that sense you can build trust between a human and a robot, and build a social team between human and robot. Okay, control issues. You have different ways how to control a team. One easy solution is to have one big leader that and send all the commands centralized, but that's not really the behavior-based approach. You can also have a complete local control and do everything decentralized. But you can also have hybrid approaches, and we fall back on organization theory to know when or what is appropriate. Several of those approaches are tried with different robot systems, examples as the Sentibot project, the NerdHerd, and the Alliance system. So The nerd herd is the one we already saw from my materials. So it's a subsumption architecture, and it had some basic interaction primitives as collisioning, following, etc. And by combining those simple interactive primitives, you could get quite complex group behaviors as flocking and cleaning up the office. On the other hand, you had the mission lab, where with it they implemented the robot schemes, say the other with it dominant architecture in behavior-based robotics. And there you select a skill for each robot. You starting to aggregate by assembling all those skills into a task. Start to generate coordination systems in the teams that you have followed, and communicate that based on a finite state machine. What's nice here, the mission lab was built for the military, so there with it they want to see a clear with it line of command, and there it's you see that directly that organization structure coming back. But also in the military, a lot of commands are not taken top down, but bottom up. So a team in the field should also be able to make its own decisions. So the finite state machine, what it looks like this, and you see here what how the different teammates are communicating via the finite state machines. Last but not least, in the hybrid example is the Alliance architecture. In principle, that's also a subsumption-based architecture a la Brooks, but it's added an extra layer for behavior sets switching, and how that was switched was based on the team coordination. And they give some very specific task to be accomplished, such as box boosting and janitor service. So there also the tasks that are not that naturally transferable to behavior-based robotics. So in principle, what they did is based on the motivation of each of the robots, you select in the different set, and the sets they activate the behaviors again. Okay, so for all that we need to able to communicate. Communication can be with it quite complex. We will see with it some examples of that later on. You can see that there are with it different types of communication. First, you can have point-to-point communication from one robot to another. You can also start shouting, and everybody that's in range can listen to you, so that's the broadcasting, etc. But what's really important for behavior-based robotics, that you can also communicate not directly from robot to robot, but also via the environment by modifying the environment slightly. You can think of others, but also putting marks on the wall, etc., etc., or just clearing a path. So a lot of with it cooperation is possible without communication. If the robot sensors are good enough to see, to grasp what the other robots are doing, then you can already accomplish quite complex behaviors. Also, when say birds are in a flock, is so much sound they cannot communicate what their intentions are, but each of them can easily see what its neighbors are doing. Another way of communicating is that you communicate not everything you see, but what you think that the summary, so the state of the world at that moment is. So you're not only broadcasting your summary of the state, but also what your attentions are, what you think is important for decisions. And that's great for sure in noisy environments, because then you only sending the essence. So last but not least is that you starting to start communicating on the goals to be accomplished. So that's say the most democratic part. But it means that you also have to have a good estimate of what the other one already knows, and that's only possible if you have good communication lines available. So a lot of this sort of scenarios are not played with real robots, but by simulations with to study multi-agent decisions. What you're then playing is a sort of games, and you then have tuples of the number of players, the number of actions, the number of the history of the actions, and the utility of each of those actions, and often also the observations to that. And then you can with it play games. You have different types of games. So some you have or one is the winner or the other is the winner. Sometimes you have win-win situations. Other times you have lose-lose situations. You have a lot of games where it's not that much in the result of the game, but if you come up with a good strategy, part of it makes a big difference if you can keep a memory of what's happened before or not. There's a big difference if you can play a game only once or twice, and so if you repeat it, do you know if you play against the same player again? So can you take revenge and learn him some lessons? So these are all different types of games you can play. The type of game that I like to play is a little bit more realistic. It's the thing that I'm active in the RoboCup, where we have cooperating robots in a virtual disaster scenario. And as you can see from the first screenshot, that's quite realistic. So what you have to do for your robots to be able to cooperate in this setting is that you have to know where you are. You have to make a map so that you're not going to the same place again and again. You have to find victims that are distributed over that area, and you have to make sure that you as robot are not doing the same as your neighbor. So you have to have distributed decision making. So that's great if you work in simulation, because then you can work in different worlds. So on the left is the DARPA, where you go over some highways. You can play soccer, you can fly around with your helicopters, or you can go into a disaster scenario. And the nice thing is that you also can use any robot you want, or a cute IBO or a cute Curio. So that has a lot of benefits. The main advantage of doing something in simulation is that you have control of the circumstances, so you can do far better experiments that are repeatable, and you know what affected your decisions. Okay, in that world there is a network team. So in this case there is one place where the human is. That's in the control room at the bottom. And he has a number of ground robots and a number of flying robots. And in principle, after disaster, you cannot communicate over the whole area. So together, they have to build up a multi-hop network where they communicate information peer-to-peer from one robot to another robot and back to the operator at the base station. So the commander has the base station and receives a map for the robots that are in the environment, but that information can be quite old and quite incomplete, and it could be that the robots in the field have more information than the commander at the base station. So how difficult it is, you can see in this video. You see here with it 4 with it cameras. 3 of them mounted on a ground robot, and the 4th one in a flying robot. The flying robot is going to explore the environment for victims, while the robot arm is looking with it where the flying robot is. Now it has found it. In the upper left there is the camera in the robot arm. And the flying robot looks back to the ground robot, and together they're going to explore this area. As you see on the lower right, you can get lost quite easily in this maze. But luckily, the victim is still moving. So you see on the right corner that the victim is found. The drone is moving and the ground robot is trying to follow. And in that way, you can let 2 robots cooperate. In the rescue scenarios, you can have 24 of those robots together. So you can see you cannot manually control that. You have to do that automatically. So we worked on that, and that's work together with Oxford and Sevilla on this sort of problems. And what we did is that each robot has to find out where it wants to go and how to extend the map. We do that by splitting up the environment into in a nearby and a far away part. So nearby is gray, the far away is white. And what they have to decide which of the 3 white areas is most attractive to go to. And in this sense, bigger is better. So you have an exploration algorithm based on utility, and the utility is based both on the area that you expect to explore and the distance to that area. Okay, then you start to cooperate between inside the teams, and you have to build up a communication network. And what you have the base station, you have the explorer robots that are on the end nodes of the tree, and in between you have relay stations, and that bring back and forward this information to the base station. So that are different roles, but the nice thing is that those roles with it can be changed. So how does it work? We have on the left the square, which is the base station, and the communication range of the 2 robots, the red robot and the blue robot. They started to explore the corridor, and at a certain moment in situation 2, the connection to the base station is lost, and 2 robots decide that the information that they got it so far, so 50% of the environment, to be brought back to the base station. So the red drives back, but together with the blue one, they have negotiated a rendezvous point in green where they will meet again. And if that's planned correctly, they will arrive on the same moment there. The blue one has seen a lot more of the corridor. That's information that the red one can bring back. and they negotiate a new rendezvous point to meet again. So the question is, how do you select those rendezvous points? What you see, the best rendezvous points you can make in an area are the places where you have to decide if you go left or right, the gateway locations, so that are indicated with the green dots here. So can you generate them automatically? Yes, you can do that by, if you have a map, you can shrink it to its skeleton, and we will see with it in the video how that looks like. Okay, if you do that in an office environment, you get nice rendezvous points on the crossings, on the junctions. But if you do it for a random environment, then the distribution can be or too dense or too sparse. So you can, with it, optimize that set by adding some extra points, or with it throwing away the ones that are too numerous. So who's exploring and who's with it relaying can change if you are in a dead end, or with it if you find a loop. And you can not only do that for with the 2 robots, but you can scale it up to 4, 8, or 16 robots. And in that way, do it. And you can make that more and more complex. So did experiments on different types of environments. So in an office environment, you see with the trottoirs that information gets much earlier to the base station, and also for random environments, you really see the benefit of this approach with exploration with relays. The same thing has been replicated with real robots, and unfortunately it's quite hard to get big enough environments to see really the benefits of it, but the same trend is visible. We showed again in video, and I will also provide a link with it downstairs to the video. So this is the type of robots that are used, and in the simulation you would see them here, and in green you see the communication range, and it's dependent on how the walls attenuate the signal, and A is bringing back forward information. You can see how you can do thinning of the environment to find rendezvous points. You can see role switching active. And you can see this together with it when you have a large team of 4 with it robots. And this is demonstrated on in simulation on 2D, but in real environments and in 3D environments, the same result applies. And as said, this is work together with Oxford and Sevilla. So, what did we learn from these experiments? That cooperation and coordination is essential if you want to explore a lot of ground, and after a disaster, that's really something you need. But if you want to do efficiently, you have to do quite some nice tricks to get the coordination inside the team working. So we talked a lot about communication. You have to think about what that means. First, you assume that your agent is rational and that it tries to get the maximum payoff. You You have to think, if you're constantly negotiating or only at regular intervals, and how to make sure that your team knows when those intervals are. If you're negotiating, then you should not come up with new information all the time. And once resolved, then you should do what was agreed. If you find new things, then you should not start doing something completely different. So you have different negotiation models, and that take turn taking over history. And what is nice, you can have a utility you try to optimize, but you can also have a negative vote where you say that doesn't agree and that it will not be done. So disagreement is the worst thing you can come to, but in some games there is no good solution, and everybody should go for its own. What's nice is that together as team you can gather a lot of information. You can even think about what sort of information you could gain in the future if you exploit certain actions. We've seen that with the size of the area to be explored. And you need a reward and utility function. Utility, you can try to predict it in advance, but in principle that estimate is less and less accurate. So typically with it you decline that. And that also has the benefit that you don't have to plan over the whole planning horizon. Each step can be modeled as a subgame where you simulate what could be the result of executing that game, and then each agent says what he thinks that sort of reward that he could gain. Okay, now games are perfect. That makes sure that you know the preference of each agent. You don't have one central point of failure that makes decisions. You have two moments of communicating. Was first to make sure that everybody knows what the state is, and also when the decision is made, what the decision is. In principle, this works fine if you have full knowledge of the world. If there are hidden parts, then it makes it difficult. But by using Bayesian reasoning, you can maximize your utilities with decision theory. So that's quite abstract. If you're going to play with soccer with your robot team, then you can see what happens. If you have a game of 5 against 5, then you can play the game with no communication, cheap talk, or a full subscription model. And they played against each other, each with their own strategy. And what you see is that if you are greedy, you lose against the rules. Strategy or rules is quite the same, but if you have an extensive strategy, then you really win. So that's a lot of nice games you could play. So then we will see what, if you want to implement that, what sort of design issues you encounter if you apply this to behavior-based models. So depends a little bit what sort of multi-robot system you implement. So DUDEC came with a taxonomy from how you could characterize each of the robot systems. So there's a big difference in team size. There's a big difference in communication range topology, if you have to build a network or not. The bandwidth that you can send over the communication line. If the team can be reconfigured, if all team members are the same, etc., etc. So Biki did it and also included reliability, self-repair, robustness, and etc., etc. And if the different teammates could recognize each other, etc. So we look some examples of research done with robot teams. So with DARPA, they started with a competition. What will happen if you have more than 100 robots? And they looked what happened, how good you could do surveillance or mapping of the environment. And they required that those teams should be operational for 24 hours without any intervention of any human. So they built this sort of robot teams with 100 robots, and you see most of them are the same, but there are some bigger robots in the back that have more capabilities. And what they did is that they could cover a lot of ground and make sure that nobody entered the building without being noticed. It's the Centibots project. So at Berkeley, they worked with an evasion scenario where you had some robots cooperating to hunt down other robots. So you had a number of ground-based robots for explorations and an aerial robot for monitoring, and they used game theory to learn the best pursuit and the best evasion scenario. So they did it with this small Pioneer with robots for the ground and some helicopter for in the air, and they played hunting games there. Now, not only America is interested in this sort of things, also in Europe, the 100+ research projects were initiated. One example is the Ice Swarm, where they looked on multi-robot coordination, and they wanted not those big American robots, but quite small micro robots with a limited computing power and a limited communication. And they built robots as small as this, but still a lot of nice results could come out of it. Okay, so what have we learned in this lesson? I give a very brief introduction of the major issues for multi-robot systems. I talked about issues about what sort of tasks you would give to these multi-robot systems, how important communications are, how the decisions are made, different organizational choices you have there. You can do a lot of the experiments by modeling the agent interaction as games, where you can allow formal decision making with it. But that relies a lot on complete knowledge. With robots, you don't have that information, but you can integrate it with sensory networks to get that information as best as possible and communicate that information again over your network. Okay, that was it for this lesson.